Okay, let's walk through the conditions for a stable circular orbit in this potential. So here's the question we are tackling. We have a particle with mass m moving in 3 dimensions under the influence of a potential given by phi of r equals minus k over r minus k prime over 3r cubed. We are told that k and k prime are both positive constants. For this particle which has angular momentum L, we want to find the necessary condition for it to have a stable circular orbit. We are given 4 options which are inequalities involving k, k prime, L and m. To figure this out, here's the plan. A quick overview of our solution approach. First, we'll define what we call the effective potential, which simplifies this 3D problem down to a 1D analysis in terms of the radial distance r. Second, we'll apply the condition for a circular orbit to exist. This happens at an equilibrium point, which means the first derivative of the effective potential with respect to r evaluated at the orbit radius r0 must be 0. Third, we'll apply the condition for that circular orbit to be stable. This means the effective potential must be at a minimum at that radius, which requires the second derivative of the effective potential with respect to r evaluated at r0 to be greater than 0. Finally, we'll combine these conditions to find the specific relationship between k, k prime, L and m that's necessary for a stable circular orbit. Alright, let's start with the effective potential. When a particle of mass m and angular momentum L moves under a central potential, meaning it only depends on the distance r like our phi of r here, we can analyze its radial motion using this concept called the effective potential, denoted as Vf of r. The potential we are given is phi of r equals minus k over r minus k prime over 3r cubed. The effective potential is always the sum of the original potential phi of r and this centrifugal term, which is L square over 2 mr square. So combining those, our effective potential Vf of r is minus k over r minus k prime over 3r cubed plus L square over 2 mr square. Now for the condition for a circular orbit which is an equilibrium point. A circular orbit exists at a specific radius, let's call it r0, if the effective force at that radius is 0. In terms of potential energy, this means the effective potential Vf must have an extremum, either a minimum or a maximum, at r0. Mathematically, this translates to the first derivative of Vf with respect to r evaluated at r equals r0 being equal to 0. So dVf over dr evaluated at r0 must equal 0. Let's go ahead and calculate that first derivative. Our effective potential Vf of r is minus k times r to the power of minus 1 minus k prime over 3 times r to the power of minus 3 plus L square over 2m times r to the power of minus 2. Now taking the derivative with respect to r dVf over dr is the derivative with respect to r of this whole expression minus kr to the power of minus 1 minus k prime over 3r to the power of minus 3 plus L square over 2mr to the power of minus 2. Applying the power rule for differentiation, we get dVf over dr equals kr to the power of minus 2 plus k prime r to the power of minus 4 minus L square over m times r to the power of minus 3. Okay, now we set this derivative to 0 at the potential circular orbit radius r0. So kr0 to the power of minus 2 plus k prime r0 to the power of minus 4 minus L square over mr0 to the power of minus 3 equals 0. To clear the negative exponents and fractions, let's multiply the entire equation by mr0 to the power of 4. We can do this assuming r0 is not 0, which it must be for an orbit. Multiplying gives us mkr0 square plus mk prime minus L square r0 equals 0. Let's rearrange this equation. Notice it's actually a quadratic equation in terms of r0. We can write it as mkr0 square minus L square r0 plus mk prime equals 0. We'll call this equation star. The radius r0 of any circular orbit, whether stable or unstable, must be a real root of this quadratic equation. For there to be real solutions for r0 from this quadratic equation star, the discriminant of the quadratic formula must be non-negative. The discriminant delta is b square minus 4ac. In our case, a is mkb is minus L square and c is mk prime. So delta equals minus L square all squared minus 4 times mk prime. And this must be greater than or equal to 0. This simplifies to L to the power of 4 minus square kk prime greater than or equal to 0, which means L to the power of 4 must be greater than or equal to 4 minus square kk prime. We can rearrange this to get a necessary condition for any circular orbit stable or unstable to exist. The condition L to the power of 4 greater than or equal to 4m square kk prime can be written as kk prime less than or equal to L to the power of 4 over 4m square. If kk prime is strictly greater than L to the power of 4 over 4m square, then the discriminant is negative, meaning there are no real solutions for R0. In that case, no circular orbits whatsoever exist. So this condition is absolutely necessary just for the possibility of any circular orbit being there. Now let's focus on the condition for a stable circular orbit. For a circular orbit at R0 to be stable, the effective potential Vf must have a local minimum at R0. This requires the second derivative of Vf with respect to r evaluated at r0 to be strictly positive. So d square Vf over dr square evaluated at r equals r0 must be greater than 0. Let's calculate that second derivative. We know the first derivative dVf over dr is kr to the power of minus 2 plus k prime r to the power of minus 4 minus l square over mr to the power of minus 3. Now let's take the derivative of this expression with respect to rd square Vf over dr square is the derivative with respect to r of kr to the power of minus 2 plus k prime r to the power of minus 4 minus l square over mr to the power of minus 3. Applying the power rule again, we get d square Vf over dr square equals minus 2kr to the power of minus 3 minus 4k prime r to the power of minus 5 plus 3l square over m times r to the power of minus 4. Now we apply the stability condition. The second derivative must be positive at r0. So minus 2k over r0 cubed minus 4k prime over r0 to the power of 5 plus 3l square over mr0 to the power of 4 must be greater than 0. Since m and r0 must be positive, radius is positive, we can multiply the entire inequality by mr0 to the power of 5 without changing the direction of the inequality. This gives us minus 2 mk r0 square minus 4 mk prime plus 3l square r0 must be greater than 0. We call this inequality double star. This is the stability condition expressed in terms of the radius r0. Let's simplify the stability condition using the equilibrium condition we found earlier. We can substitute the equilibrium condition into the stability inequality in two ways. First, substituting for L squared R0 and simplifying the resulting expression yields the condition that mkr0 squared must be greater than mk prime. Dividing by mk, this means r0 squared must be greater than k prime over k. Alternatively, substituting for mk prime leads us to the condition 2mkr0 squared minus L squared r0 must be greater than 0. Since r0 is positive, we can divide by it. Rearranging the result gives us 2mkr0 must be greater than L squared. Thus, we find that the circular orbit is stable if its radius r0 is strictly greater than L squared over 2mk. Now, let's combine the conditions. The radii of the possible circular orbits are the roots of this quadratic equation. Using the quadratic formula, we find the roots for r0. For a strictly stable orbit to exist, we need two conditions to be met. First, there must be at least one real root for the radius, r0. This means the term under the square root must be non-negative. Second, at least one of these real roots must satisfy our stability condition, which requires r0 to be strictly greater than this threshold value. Now let's examine the different cases based on the value inside the square root. If it's negative, there are no real roots, meaning no circular orbits exist at all. If it's exactly 0, we get one real root for the radius. However, this root is exactly equal to our stability threshold, meaning it corresponds to a marginally stable orbit, not a strictly stable one. Finally, if the term inside the square root is strictly positive, we find two distinct real roots for the radius. The larger root is given by adding the square root term. Because the square root is positive, this radius is strictly greater than our stability threshold. Thus, the larger radius corresponds to a stable orbit. The smaller root is found by subtracting the square root term. Since the square root is positive, this smaller radius is strictly less than the stability threshold. This root does not satisfy the stability condition, and it corresponds to an unstable orbit, much like an unstable equilibrium at the top of a hill. So, for a strictly stable circular orbit to exist, we must have two distinct real roots for r0, and the larger one will be stable. This requires the discriminant to be strictly positive, not just non-negative. That means L to the power of 4 minus 4mi squared kk prime must be strictly greater than 0. Rearranging this inequality, we get L to the power of 4 is strictly greater than 4mi square kk prime. Or expressed the other way, kk prime must be strictly less than L to the power of 4 over 4m square. And that brings us to our conclusion. The necessary condition for a stable circular orbit to exist is that kk prime must be less than L to the power of 4 over 4m square. Let's compare this with the given options. 1 kk prime less than L to the power of 4 over 4m square 2 kk prime greater than L to the power of 4 over 4m square 3 kk prime less than L to the power of 4 over m square 4 kk prime greater than L to the power of 4 over m square. Our derived condition exactly matches option 1. So the final answer is option 1.